Hello, this is the second part of Jeffrey McCracken and Caleb Unger's video. And to start, I'm going to show you the ordinary differential equation from the Lotka-Volterra model that we derived from Konkuk's University and Smith College's example data that they gave in their PowerPoints for a Lotka-Volterra model considering a rabbit and wolf population. These are the coefficients that were relatively determined to capture the behavior of the system. And then we went and derived our data over a time span of 500 periods, with the initial rabbit data being 1,000 and the initial wolf data being 40. And we called our function, or our function name, ISE wolf rabbit, and then derived it with the ODE function in MATLAB. And what this did is it gave us populations in the variable p, and we assigned those as pop1 and pop2, which is our rabbit and wolf populations. Upon reviewing this model, the professor and myself looked and derived a way to formulate inputs and targets for an autoregressive neural network that takes an external input. And so to do that, we made our inputs the two populations and made our targets the sum of both populations. And in so doing, we were able to train our network. The network that we would use would be the nonlinear autoregressive with external input, or NARX. And through this, like most methodologies, you would go in, put your inputs and your targets. You would specify how much you wanted training, how much validation, and then you would specify your neurons and your number of delays. We had one delay and I think 8 hidden layers or hidden neurons, so that's what we selected for our neural network. And then you would train the data. I'm not going to train it here just because we've already done that. And then after training, you would see the accuracy of your model, which was fairly well, and then you would generate a function. Now our focus is to see if this function generated by the neural network captures the relationship modeled in the Lotka-Volterra model. This is the function that MATLAB generated, and one of the things I highlighted is that the input data was cellular data, so you had to make sure that that was cellular data. It's a cell, and so it was a 2x1 input for each cell corresponding to the time steps of the data. And since we're only having one delay, we only need another variable that is just a single 2x1, which represents one delay back as an input in order to see if we can capture the behavior of the model. Then we had to format our data that we were going to put in. Our first scenario, like I said, was the exact data we used to train the network. And to do this, again, we put our inputs as our populations that we derived with the ODE function, and then our targets as the sum. This is how they trained the data, and this is how we formatted our cells. This is how we got our cellular data for our X and for our X1, which the X1 is, or the XI1, I apologize, is the initialization or the one delay back. And then our output would be in the format of the total population, which is derived from our equation, wolf-rabbit neural network, that I just pointed out, that was generated by the neural network application in MATLAB. So I'm going to run this code, and then we graphed what it would look like. So as you can see, the network does capture the behavior relatively well. The reason why they're closer together than these peaks are is because this is 113 time steps over a period of 500 time units. Granted, this took the time steps as literally one step, so this is over 113 time steps, while this is over 500, yet it is still 113 time steps. For this reason, this models this very accurately. It just shows it condensed. Then with the help of my professor, I was able to also run this neural networking model through some testing data that was sampled towards the end of our two populations. And then we were able to format this much the same way and then plug it in to our neural network down here. So once we perform this test, we see that, yes, the sampling size was only 20, and we see that the values do not continue up this way because that's not the data that we fed it. The data that we fed it was somewhere down in the trough area, and according to our neural networking function, it is capturing the cyclical behavior of it about to climb again up towards the kind of capacity that we've seen. This shows that it doesn't matter where the data comes from, as long as it's accurate or indicative of the system, the neural network will pick up on it. Our last model, which I'll just go ahead and run to show you that it does not capture the behavior very well, was derived from an ETS model in R. The reason this does not model it accurately is because that the ETS model in R only captured the ever-increasing trend of the data and not the cyclical pattern. We tried Holt-Winters and we tried ARIMA, but ARIMA would only give us a simple naive method because it could not pick up on the other behavior, and then the Holt-Winters would not even forecast it because it says it wasn't seasonal data, and it's not. It's cyclical data. And what this shows is that it will initially pick up on the behavior of the system as the forecast originally does. However, when it's supposed to cycle back through like we saw before, it just keeps increasing as the data was indicative of in the forecast that we generated in R. I'll show you how we derived the rabbit ETS and the wolf ETS data. And what I did is I took the data generated by the ODE45 function and saved it into a CSV file, and then I read the CSV file into R and then assigned that as a time series to a variable called wolfrab. And using that time series, I then forecasted out 113 periods, which I just showed you, using ARIMA and using the ETS model. The ETS model, as you can see, has the multiplicative, the additive, and then not part because it's not seasonal for each the wolf-rabbit data. And then using this data, I then wrote it out to another CSV. I assigned the wolf-rabbit ETS variables in MATLAB, saved them, and then input the data forecast from the R platform into this, and that is how I generated that data and plugged it into my network to show that a relatively accurate forecast or idea of future data in such a system is necessary, lest it initially capture the behavior but then kind of converge on a point and keep increasing without showing the cyclical pattern of the data. This shows that our neural network does capture the behavior of a predator-prey system as long as the data is indicative of the system that you trained the network with originally. Thank you for your time and have a great day.